Hello everyone, in this video we are going to demonstrate genetic algorithm implementation using Python programming language. This demonstration will utilize dataset obtained from public data provided by Kawal COVID-19, which provides up-to-date data about COVID-19 cases in Indonesia. For the demo, we only take 52 data points spanning from the 1st February until 24th March 2021, and then store the selected dataset on our own storage. Next up, after we load our dataset, we are defining our objective function using an autoregressive integrated moving average or ARIMA model with the order of 110 to predict the cumulative COVID cases at day t, specifically at day 51 and day 52 of our dataset. The formula is given as follows: y hat t equals to mu plus yt minus 1 plus theta 1 times yt minus 1 minus yt minus 2, where y hat t is the prediction number of cases at the t, mu is a constant white noise, yt minus 1 is the number of cases at the t minus 1, theta 1 is a constant, yt minus 1 the number of cases at the t minus 1, and yt minus 2 is the number of the cases at the t minus 2. And then we are defining our fitness function using mean absolute error or MAE, which are represented in the following equation, where MAE equals to sigma E I1 until n absolute yi minus xi divided by n, where yi is the prediction result of the COVID cases at day I, and xi is the observed or the real number of cases at day I. And then we can implement our fitness function. Here we define it as fitFunc with one parameter predicted, which contains the prediction data of 50 days, and then we are initializing the total absolute error or total AE as 0, and then for all the values in the prediction list we calculate the difference between the prediction value and the real value, and then we are adding it to the total AE. And after that we can get the MAE by dividing the total AE with the length of the prediction value, which is 50 number of value, and we are returning it with 1 divided by MAE, because the smaller the error means the better the fitness. So after implementing our functions, we can move to the next step by defining the population size or pop size. Here we define the pop size by 15. After we define the pop size, we can then generate the population. We are using a random function to populate the population. Here for x in range of the population size, which is 1 for until 15, we then calculate the random for the mu and the theta, because we are going to optimize the value of mu and the theta. For the mu, we are using the random integer in the range of 10,000 to 30,000. As for the theta, we are using the uniform random from 1 to 5 and then rounding it to 2 decimal number, and we can see the population that are generated below the code. After we have initialized our population, we can evaluate each individual by applying their values to the ARIMA function. First, we need to build a two-dimensional array to hold the values of the prediction of each individual. So the first index in the predicted array here is the index of the individual, and then the second index here is the index of the prediction value. Here we initialize the first index by the length of population, which is the number of individuals equals to 15, and then initialize the second dimension or second index with the 50 0. So we have a 50 prediction place. And then because we are using the ARIMA with t-1 and t-2, so we are going to predict from day 3, and here we are going to initialize the first day and second day the same with the original data. So we are not predicting the first and the second day. And here the first day is index 0 because array starts at 0 index, and the second day is index 1. And then starting from index number 2, we are going to predict the number of cases in day 2 by applying the ARIMA. Using the population index here means the population index is the individual at index as a certain index. For example, if index 2, then it means it takes the value of the third individual, and here we can see that it is this 1, 2, 3, index 2, and here the index 0 means the mu value because the mu is in the index 0, and then here the 1 index is the theta value. So as we have defined before, that the ARIMA function accepts 3 parameters, the mu here and the theta, and then the x or the third index that we are going to predict. So after we are running these loops, we can get the prediction for 50 days of a specific individual in this index. And after all the loops is completed, we can get the prediction 50 days of each individual. Then we can plot the prediction result using a plot function like this. So we can see that how is each individual prediction looks like in the graph. So here is the prediction from the individual 1, individual 2 until individual 15. Okay, so after that we can check the MAE of each individual by applying the fitness function that we also have defined before. So we initialize fitness with 0 arrays with the length of the population, and then for each individual we are going to calculate the fitness function, which is the predicted array that we have get before of the specific individual in this specific index. Then after that, the fitness function will be calculating the fitness value and round the value to 8 decimal number or decimal places. Then we can see Here are the fitness value of each individual from individual 1 to 3, 5 until individual 15.
Okay, so we continue to the next process. The next step will be the roulette wheel process before we continue to the crossover. So in the first, we show the population data with the fitness value, just to remind about our data. So this is the code, and we can run it. As you can see, the result will showing the population, included the fitness value for each population data. And then next process is we define the PC, probability of crossover. In this case, we decide to use PC is 80%. So the calculation is, as you can see, 0.8 multiplied by length of population. In this case, the population size is 15. So we run the calculation, and the PC result is 12. So in the next, we shuffling the data and choose the 12 data for the crossover. And then the next process is we generate the roulette wheel selection. So this is the code. We list and zip the data pop and data fit. As you know, in the above, data pop is filled with population and data fit is filled with the fitness. So we zip and we do the random shuffle of the list that include data pop and data fit. And then we do the random choice of list to the specific length is count of the PC. So in here PC is 12. So the random result will be showing the population and fitness function in 12 data. We can run the code. So as present below, now we found the selected individual or selected data after we do the roulette wheel selection, and this data will be used for the crossover process.
In this video, I would like to continue the genetic algorithm process. After selection process, we go to crossover process. In this process, we create a procedure called crossover with the parameter is population. This population is a result of the selection process. Result from the selection process. First, we sort the population to selected pops variable, and then we calculate the number of offspring from that population. And next, we calculate the number of selected pops. Next, we declare the offspring variable as an array, and then we declare the available individual as an array with value the number of index from the population array. So in this in this array, the value is 0 until the number of population. And then we declare the alpha because we use a single arithmetic crossover. So we use alpha 0.8. And then this variable for store the random value from number 1 until number 2, because in this program we use two genes is mu and theta. We use mu and theta and crossover the value between another parent to get the offspring. Next, we go to this line. This is the code for print the population before crossover process. And then next, in this section, this is a looping process for choose the index of individual in the selected pops variable that we wanna calculate to get the offspring. For example, in this code, in this line, this is code for get the index from 0 until the number of selected pops number. We choose one index, and then we store it to get individual one. Next, we go to while true loop. This is the while do, or this is the process to check that individual number 2, the index of individual number 2 must be different from individual number 1. So in this line, we use condition that individual 1 it's not equal with individual 2. If not, this process, this loop will looping again to get the number that different with individual 1. After we got the number that different with index of individual 1, we must remove that index from the array, available individual array. Why? This is for max loop. We not get the same individual to make a pair and get the offspring, because we must pair each individual without duplicate. Next, in this code, random parent 1 and random parent 2 is the process to get the value from the selected pops with the number of index that have we get before. And then we store all the value of the selected array. There is two value, mu and theta, from parent 1 and mu theta from parent 2. Next, in this condition, if the cross point is equal with 1, we will do this code. The cross point value, we got it from this step, random process from 1 until 2. This is the process that we will decided the location of the genes that we want to calculate to cross the genes. If the cross point 1, so the mu value will be crossed. And for mu value from parent 1, we calculate with this formula, mu parent 1 times 1 minus alpha. Before we declare the alpha is 0.8, so mu parent 1 will be times with 0.2 plus mu parent 2 times 0.8. And then for the mu parent number 2, the new value of mu parent number 2 is mu parent number 1 times alpha, or 0.8, plus mu parent 2 times 1 minus alpha, or 0.2. After that, we got the new value of mu from each parent 1 and parent 2. Then we insert that value to the offspring variable. So this is the the offspring number 1 and number 2 from first pair of individual, or from first pair of the parent. Or else, if the cross point is 2 or not equal with 1, the genes that will be crossed is theta. With the same calculation, with the same formula, theta from parent 1 is the theta parent 1 times 1 minus 0.8 plus theta parent 2 times alpha, or 0.8, and the new value from theta from parent 2 is theta from parent 1 times alpha, or 0.8, plus value of theta parent number 2 times 1 minus alpha, or 0.8. For that, we append all the value to the offspring variable. For one loop in this process, we will get to offspring. So this process will loop until the total of individual divided by 2. If in this program there is 12 individual, so this process will make a loop until 6 times. And then the next process is the offspring result. Actually, this process just called the procedure that have we created before with the parameter from selection process. And this is the result of the crossover process. You can see the first, this section is the individual that result from selection process, and next this is the mu and theta value after crossover process. Thank you. This is crossover process, and next we will be continue with mutation step.
Hello everyone. I'm going to continue from crossover to mutation. As my fellow colleagues have done the other steps, so I'm going to explain my part of mutation step. So I hope you can see what's happening on my screen. So this is the result from the crossover step. So this is crossover genes before the offsprings, before mutation, before crossover. Then these ones are after crossover. So on this code, I'm just extracting the offspring result after crossover. And these are the results. As you can see, this result is the same as this result as well. So I just extracted the same offspring after crossover. So I just extracted the same. So now this is the code for mutation. So for us to do mutation, we have to know the genome size. And the genome size is the offspring, number of offspring. Offspring result times the number of genes. So we are going to multiply by 2 because we use gene 1 and gene 2 and we get 24. So it means the new offspring will have like 24 genes. So we also have to define our probability of mutation. And in this case, we assume to take it as 10%, which is 0.1. So from this, I am initializing the offspring result to mutation result. So then I also initialize genome size, which is the length of offspring result times the length of offspring result, which is how many genes we have, which is 2. And also here I initialize the probability of mutation, which is 10% and is equals to 0.1. So here the number of mutation is going also to be a real value. For us here, we are just changing the real value into int value. So the probability of mutation times the genome size, and we are also putting or letting the system know that the result is supposed to be 0 decimal places for it to be our int. Then we have the for loop here. So this for loop, what it's going to do is to randomly select 2 genes to be muted. So this is, we have to know the position of mutation, like which position of the gene that is going to be muted. So mutation position we randomize, the gene size. They range from 1 to gene size, which is 2. So meaning we are going to have 2 positions. So we initialize the individual index, which is mutation position, divided by offspring result. So mutation position, for example, if we get 7, we divide by the offspring result index, which is 2. So 7 divided by 2, it will become 3.5. Since we are saying to 0 decimal place, it will round it and give us our integer value, which is 4. So what is going to happen is we are going to have 4, but as we can see from these results, the first index, which is 00, this index 00, it is 26,470, and this 01, it has like 411. But we are supposed to know, like, if it has a leftover, like if it has a remainder after dividing, after the division from mutation position in the offspring side, like 7 divided by 2, it has like a remainder, then it's supposed to be placed where. So we need to divide because it gives us this row, which is 00 and 01. So we need to divide the result so that we know either it is from 00 or it is from 01. So from here, that's when we are saying leftover, we want to know like the modulo. So mutation position modulo, then length of offspring result. So the leftover, like if it is not equal to 0, which is like maybe we get the position is 6. So we divide by 2, we directly get 3. So 3, it doesn't have remainder or a leftover. So it's equal to 0. So it means the value will be mu. So the mu will be randomized from 10,000 to 30,000 for us to have the new mu. So if it's divided and we don't have a 0, so it means the value is in this zone, because this column is for mu and the ones with 4.11, 2.45 is for theta. So if we divide and we don't get 0, so it means it is from the mu side. That's why we are also randomizing from 10,000 to 30,000, because you can see the value there are 26,000, 28,000, 14,000. That's why our range is 10,000 to 30,000. And also we have our new mu, which we are going to place in this index. This index will always be either 0 or 1 or 2. So 10, 20, 30, which means it is in the column of mu. Or else we have to know the value of theta, or we have to calculate the new value of theta. So this one we randomize again from 1 to 5, and we just allow 2 decimal place since it's a real value. So it will be like here. So for example, like I said, like if we divide like 9 divided by 2, then we'll get 4.5. So from 4.5, the value is not equal to 0, but like we have a remainder. That's why we will have, that's why we will know like the value is going to be placed in the new theta. So the theta value will be placed in this array, which is 1. Before for mu, it will be 0, but for theta, it will be 1. Since I said before, like this column, it represents this column of 411245, it represents theta. So we randomize it from 1 to 5, because also the values there from 3.2, 2 point something, 1 point something, 4 point something, and so on. So the new theta will be stored in this array. So this is going to print the mutation result before being muted. And this one is going to print the mutation result after the two genes that are going to be randomly generated or randomly selected, and the two genes are going to be muted. So this is the result that we get, and if we compare, we have this two, and this is the same, this and this is the same, this and the same. So we just want to know which two genes have been muted. So if we can check from here, we can see that the gene is different. The gene before mutation is different from the gene after mutation. So it means 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it means offspring 5, gene 2 have been muted. So we continue to search to see. So if we can check here, it's the same, until we come to this one, the last one. It's 2.3 and now it's 4.54. So we know that this is the second selected gene that have been muted, which is the 24th gene, the offspring 12 gene. So this is the result. Thank you.
I'm going to explain the last step of the GA, which is to iterate the GA until a certain threshold. In here, we use the threshold of generation, how many generation. Here we define the number of generation to be 50. And then we are initializing empty last generation data, which will be filled with every iteration of the last generation. And then we use the for loop in the range of the generation number, which is 50. And just like explained in the previous part, in here we just summarizing the steps and put it in iteration. First one is calculating the city using the current population. So here we, just like the previous part, is the same. We put it here using the ARIMA, and after we get the prediction, we then calculate the fitness of the population. And after we get the fitness, we then do the roulette wheel using the prediction and the fitness value. And then we shuffle the roulette using the stuff. And after that we get the selection using random choice. So we pick the how many individuals in here using PC, which is 12, which already been also defined before. So from 15 individuals in the first population, in here we reduce it to 12, and from each of these new individual we do the crossover using the function that already explained before, and from this crossover we get the offspring, and we also then mutate the offspring using the mutation function before too. And then after we have the mutated offspring, we do the prediction using this offspring. And after that, we also calculate the fitness value. And after that, we get the best 15 individual by combining the current population or the parent and the offspring into one complete list. After we have all individual in the current generation, we then sort them reverse, so we get the one with the best fitness value on the first row, on the that's in the first the first data. After we have them sorted, then we select 15 here using array selection from 0 until the population size, which is 15. And after we get the new population, we then extract the population data, because here the new population contains population data and the fitness, but for the next iteration we just need the population, there's the individual data. So we take the individual data and put it in the population data, so the population gets updated. But then we also store or keep the last generation, the complete data too, in the last gen variable. And then it is iterated until 50 times as we define the generation number 50. And after we have done iteration, we can see this is the composition of the individual and their fitness value of the last generation. Yeah, from here we can infer that the iteration is converging, as we can see the individual became all the same with the same mu, theta, and same fitness value. And then using this last generation data, we perform the final prediction here using the same procedure as previously defined. And after we get the final prediction, we plot it to a graph and we showing the exact number of prediction of day 50 and day 51. Yeah, here we can see that the graph is, well, not exactly similar, but it is moving on proper, the same direction as the real cumulative chart. So I think that's all from our group about the implementation of genetic algorithm using Python programming language. Thank you.